So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Of advanced computer architecture CS203. So if you watch the first lecture, you should remember that we talk about the most important abstraction, the most important concept behind modern computers is this von Neumann architecture. So what von Neumann says that is that if you want to have a computer that is reprogrammable, by reprogrammable, oops, what's up? By reprogrammable, it means that the computer is able to perform different functions if you and without the need of changing the hardware configuration. So before the von Neumann architecture, if you want the computer to perform a completely different function, then it requires you to reconnect those wires, reconnect those tubes or vacuum tubes to perform different functions. However, with von Neumann architecture, those are not necessary. So a lot of you are thinking about computer architecture is about hardware. However, let me tell you one thing. Without von Neumann architecture, the whole software industry is not possible because it's whenever you want to change the function of the computer, you have to reconfigure the hardware. However, the contribution of von Neumann architecture is that von Neumann say that if you want to have a reconfigurable computer, all you need is a processor, microprocessor, and memory. And he didn't say persistent storage, but it's actually a must in modern computer, because after you create your program, we need a place to store the program persistently so that whenever you need that program, you don't need to rewrite it on the fly, recompile it on the fly. So what inside a program are instructions and data. And whenever you want the program to perform the function on this computer, you just need a system, for example, the operating system, to load your instructions and data into the system main memory, and your processor would fetch instructions from the main memory and then looking over what the instruction wants us to do. So if the instruction wants us to access data, then there will be an operation between the processor and the memory to move the user data, or say the runtime data, or the data that the program needs to use on the fly. And then using that data or doing whatever the instruction wants us to do. And after we finish executing that instruction, let's just move forward to the next instruction, continue the execution. So the beauty of von Neumann architecture is that just loading different programs into the computer, into the main memory, your computer can perform completely different functions. So no matter what programming languages you are using, for the C programs, you have to generate the machine code as instructions, and you also have to encode your data as part of a program. And if you are using external libraries, they are already in a format of machine object, machine libraries, machine binaries, and just just link them together into your program. And whenever you need to execute your program, again, the same process of von Neumann architecture just work. And for Java, still follows a similar strategy. However, the big difference here is that for Java, we compile it into bytecode, which is a different type of a machine code. And this machine code is only understood by the Java virtual machine. And the Java virtual machine would dynamically link classes and your compiled classes together and put together of them and create the binary that your underlying machine can understand, and again, put them in the main memory. And the rest of them, the execution is the same as the von Neumann architecture. And for Python, Perl, this kind of interpreter-based language, again, the interpreter would generate the machine binary on the fly and send it to the main memory. And this is how the program gets executed. So no matter what programming language you are using, the backend is always the von Neumann architecture. So, and the whole purpose of this class is to tell you how to best utilize the von Neumann architecture, the von Neumann computer that you own. So first of all, we have to talk about what is performance and what affects each factor in performance. So talk about the definition in performance. And I believe you guys already have already done some of the readings through your reading quiz. And as I mentioned, this class, we are going to use peer instruction method, which is an active learning method that you will require to read something before the lecture. And then I will bring activities, and these activities would involve in several processes. First of all, I will ask you to individually think. And then after you think, let's see your understanding about this topic, and then we go into the group discussion and the whole classroom discussion. So as a practice of this process, let's start by using this first reading quiz. And now, the pop-up quiz. And now I'm going to create a pause through through Zoom. So you will have 90 seconds now to select the answer. And if you need, and depending on the completion percentage of completion, I may extend the time. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to the current poll, I saw there are 2 popular answers. So it's definitely a case that there's no consensus within the whole class, and we have the demand of discussing among you guys. So now, because there are some limitation in Zoom. So for example, when we go into the breakout room, we are not able to see the slides anymore. So what I want you to do right now is that go to your chat, and then I just sent out a PNG file, and the PNG file contains the question that we just sent it out. So if you are done with opening the PNG file, just use the check mark in Zoom and let me know that you are done, and then we can go forward. Did you see the PNG file? Open it, open it, and pull the question. And don't worry about the correctness of your first bolt, because we are just because these questions, they are designed to make you wrong. So if you get it wrong, that's okay. But and we just treat the correctness as a bonus in team in a group discussion. So if you get it wrong, it won't affect your grades. So don't worry about the correctness of your first bolt. However, I do encourage you to discuss your friends. Okay, so if you have opened a file, just use the check mark. I only see 13 of you open a file so far. So if I don't see sufficient amount of them, I think we are going to stall here forever. Yeah, if you are done, just use the check mark. Okay, so now I guess most of you have it. So the next thing I want you to do is that after entering the breakout room, elect someone as your scriber for today. So whenever I chose the team, that person will be responsible for express the thoughts and the answers in your group today. And so that will be the scriber. All right, so now, and once your group reaches a consensus, go back to the main lobby and vote. And now let's try to wrap up everything in about 3 minutes. All right, when you are back, just vote. And you have 15 minutes to vote your answer. Seconds, sorry. All right, that's 5 seconds. 5, 4, 3, 2, 1. Time is up, 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 up. Okay, one of you hasn't voted. Okay, so all right. So some of you ask you about the breakout numbers correspond to the team numbers that you received. For most, I believe yes. Okay, so now let's look at that. Okay, so now, let's do this. So first of all, who are the scribers? Who are the scribers? If you are the scriber, please raise your hands. Raise your hands. Like, I didn't see anyone raise the hand. There's a raise hand function, I believe. You are the scriber, raise your hand. Okay, I have Joe. What else? There are 4 teams, so there are supposed to be scribers. Or if your team doesn't have a scriber, so except for scribers, well, okay, so Jonathan, you are one of the scribers. Who else? All right, so if you don't have a scriber, at least someone in your team that is elected must be telling us your answers. So, oh, Andrew, okay, you are the scriber. Who else? All right, so now we have three scribers, but not sure if I will get the team. So the way how we chose the team to answer the question would be, we do random stuff like this, and whenever I click, okay, it looks like we are having team number 2. So who, and looks like the scriber for team number 2 is Andrew. So can I have Andrew sharing your thoughts about this question?
Okay, our team thought the answer should be B.
Okay, so how did you get the answer?
I think by the formula that the
What's the formula?
equation is CPI times CT times IC, which is the instruction count times the cycle per instruction times the cycle time.
Okay.
So here we have 5 times 10 to the 9 instructions.
What's the 5? Okay. Okay. So actually you are saying about you are starting with instruction count times CPI times cycle time, right? And the instruction count would be 5 times 10 to the 9. And what's the CPI?
The CPI calculated in average way. So we have 20%. 20% of the instruction are CPI of 8. So 8 times 20%, which is 0.2, and 0.2 times 4 for the typing instructions. And the rest of them are 60%, which is 0.6 times 1. So the average CPI we got here is 3.
Okay, so this one is 3, right? And what else? What's the cycle time?
And the CT should be 1/3 gigahertz.
Right. So the thing is that the cycle time is the reverse of your frequency, right? So gigahertz is the frequency, right? So if you cancel this out, right, and then you will figure out, and because gigahertz is 10 minus 9, so it will be 5 seconds, right? So great. So now I believe all of you are familiar with and thanks, Andrew. So looks like the blue team right now got a point, right? So and thanks for all others. And let me see how to put all your. Okay, so now let's look at so that's let's have an overview of this. So the performance equation, which you probably already learned from the reading or a long time ago in your undergrad computer architecture class, is that we define the performance as 1 over execution time. So that's why when I ask you about the execution time, because when we define the performance, we have to first know we have to first know the execution time. And because the shorter the time, it means the faster the computer is executing the program. So the performance is defined as 1 over execution time. So, and the execution time is instructions per program, how many instructions per program, how many cycles per instructions, and the seconds per cycle. So, and usually the seconds per cycle is 1 over your frequency. And the very fast way to calculate this is that 1 gigahertz is actually 1 nanoseconds. So if you have 2 gigahertz, that will be 2 nanoseconds. And in our short representation, usually we use instruction count IC to represent instructions per program, and cycles per instruction CPI to represent cycles per instruction, and a cycle time to represent the last part. So that's the performance equation. So with this, we use execution time to define the performance, and usually measured in seconds. And you might be curious how this formula comes from. And if you remember the big picture, the von Neumann architecture that we talk about, it's actually not too difficult to understand. So as we said, your processor is queued instructions by instructions, and usually the execution of instruction is controlled by your clock. So how many the total amount of instructions that you need to execute in your program will decide how many of these instruction instances that you have to go through to finish your task. So how many of this and how long is it take to execute one of this would give you the performance, right? So how many of this, that's instructions per program, and how long is it take to execute each of that? That will be cycles per instruction times seconds per cycle. So if you have the big picture of von Neumann architecture, it's not too difficult to understand the performance equation. And as Andrew just mentioned, this is the way how we derive the answer as 5 seconds. And when we talk about the CPI, because your program will have a composition of different types of instructions, so it's the average CPI. And you should be aware whenever your composition changes, it will give you a different average CPI, even though it's on the same machine. All right. So now the second part, the second question that I want to ask you is, what is the so if I have 2 machines and the machine X is the same as the previous question, so I have another machine Y. So for this machine Y, how much faster is Y over X? All right, so now let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now let's look at to get familiar with, well, to have you get familiar with the process. So let's first look at the poll result, and it looks like D is the most popular answer. However, is less than half. So definitely we should go into discussion, and you should be able to find the question through your group chat. So go through the group chat. I sent out an image on about before Henry Wu's question. So just check that question and then open it. And now we are going to have a group discussion. All right, after you are back from the main lobby, vote as soon as you can. 5, 4, 3, 2, 1. Time is up. Okay, so now let's look at what you guys think. Okay, so looks like after the discussion, wow, 86% of you think is D. So right now I want to have a group to share your thoughts with us. Wow, so this is a mistake again. So let me see if I can, oops. Okay, so this is probably two. Okay, so now group 3. So who is team 3? Who is the scriber of team 3? Raise your hand. Who is the scriber of team 3? Raise your hand. The red team. If you don't raise your hand, I will give the chance to another team. Who is the scriber? Okay, Daniel. Hello? Hello, Daniel. Your voice doesn't sound right. Oh. Hello?
Hello?
Hello? Okay, finally. Works. What do you
Hello?
think? Hello? Yes, I can
Hello?
hear you. Yes, I
Oi.
can hear you now. Yeah, we can hear you. You are okay. You are okay.
Oh, you can. Okay. I guess I can't hear
Yeah.
you.
Yeah.
Oh, there we go. Now I can hear you. So the speed. Oh, so we got D, and the reason for it, I think, was on page 49 of the textbook. We got the execution time for machine X being 5 seconds, and the execution time of machine Y being 4 seconds, using the same approach from the last problem. And then the speed up is either the performance of the enhanced system, so machine Y over X, or the performance of X, or we have the execution time of machine X over machine Y, which is what I did, and it comes out to 1.25.
Okay, so it's machine X over machine Y, right? So that's how you get 1.25. Okay, so that's actually how we get, thanks, Daniel. So that's actually how we calculate it, right? So here's the thing, right? When we talk about performance, it's really important that everyone has a consensus. So one example I like to say is that a lot of us, it's not being racist, but a lot of us are coming from an Asian family, and sometimes the annoying part of an Asian parents is that they always like to compare their kids. So for example, they always say that, hey, my kids is doing well, he's better than yours, right? So but when we say better, the better has no strict definition about what is better, and that's not science, right? So for a computer scientist, we define the speed up as the relative performance between two machines. And when we say Y is n times faster than X, here's our definition. It's always the baseline system over the execution time of the improved system. So the n could be smaller than 1. If n is smaller than 1, it means that the later system is worse than the new one. However, if it's greater than 1, it means that the system enhanced the system performance better than the original one. And the speed up of X over Y, Y over X, is always the execution time of X over execution time Y. So that's the definition. And don't try to argue with me, yeah, we can do this, we can do this, we can do this. No, that's the definition, right? So that's the definition. It's like, okay, this is the English word for performance, right? And there's nothing else can say, right? This is the word performance. You cannot change it. That's by definition. So the only definition of speed up in computer architecture is execution time of baseline, or say X, over the execution time of Y, the enhanced system, when we talk about the speed up of Y over X. So if you look at this, the speed up of Y over X will be the execution time of Y will be the execution time of X divided by the execution time of Y. So that will be 1.25. And looks like after the discussion, we all got it right. So now, knowing the basics is not enough being a grad student, and it's more important for you to understand what would affect each factor in the performance equation. So now, all of you, a lot of you are from the computer science department. Even though you are not in computer science department, you are writing programs every day. So now I'm asking you, being a computer scientist, computer engineer, being a programmer, how much you can directly affect. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like B is the most popular answer, but C is also popular, and some of you chose A and D, right? But and so it's definitely a case that we should discuss with all of your friends. So now what I would encourage you is to open the file and then go into the discussion room. Wait, how come? Sorry.
Professor, we got sent back to the main session.
Yeah. So because I think there are some issues here. So give me a second, and I'm supposed to be able to send a broadcast message, but it looks like we can't. Let me do this real quick. Okay, so it looks like there are some issues with the assignment. So, okay, so now we are good. So go ahead and start the discussion again. All right, so that's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now looks like if I guess it right, one group think it's C. One, maybe two groups of you think it's 2 or 3 groups think it's B. So I do want to encourage some of the group to share your thoughts with us. So now that's C. Okay, instinct. So that's group number 1. Who is the scriber? Can you raise your hand? Let us know. What do you think? Okay, so Golden. Let me see. How can I? Okay, so wait. It's so okay. Golden.
Yeah, hi.
Hi.
So we think the answer is B,
Okay, so which is the one?
the instruction count. So
Okay, so
yeah,
why do you think that's the right answer?
so cycle time is totally dependent on the processor design, which we had a similar question in the reading quiz. So, and cycles per instruction is dependent on both the instruction count as well as the clock time, cycle time. So the only thing that is
Okay.
totally dependent on programming is instruction count. So that is why we
Well,
think.
so this is the question is not saying totally depending on, right? So it's saying what a programmer can affect, right? So if
Yeah.
you read it in this way, you still think it's the IC is the only one that you can affect. Okay.
I mean,
Okay.
that was what we
Thanks.
discussed
That's
in the
the
group. So
okay. So that's the response from instinct. Is there any other group has different thoughts? Raise your hand. Okay. So I have Joe. Which group do you represent?
Group 3.
Group 3. So that's the Valor. Okay. What do you guys think?
We think that we think as programmers we can affect 2 of the 3 factors.
Okay. What are the 2?
The instruction count and the clocks per instruction. CPI.
Okay, so the cycles per instruction, right? So the instruction count and
instruction.
CPI. And so in addition to instruction count, why do you think you guys can affect the CPI?
We can, I think by exploiting instruction level parallelism, we can add more instructions. We can directly affect the clocks, the cycles per instruction. We can reduce it a little bit at least. So in that term, we can affect the CPI directly as a programmer.
Okay, thank you. So now, before I announce the answer for this question, right? So let's just go into another discussion, another question first. So look at this 2 pieces of a code. Okay, so first of all, I need to have a demo, right? So for this 2 pieces of a code, so the left-hand side, so if you look at these 2 pieces of code, the only difference is basically adding 2 matrices. And the only difference of these 2 pieces of a code is that the first, the version A, it starts with I equal to 0 and iterate on I. And the second part, and the inner loop iterate on J. And the other one does the flip, right? So let's look at the performance of this, right? So oops, I think I have to share. Oops, sorry, I am sharing this one. Okay, so let's look at that, right? So okay, so you guys are seeing my screen now. So I have this code and matrix add.c, and as you can see, this is the initialization part. And this is the, so I have 2 versions, right? So I will compile this program into 2 versions. And if for version A, that's the left-hand side, we start with for I equal to 0, and then for j equal to 0. And the other one does the reverse, right? So let's have a demo of it. and see what's the performance of this. So let's run the MADD-A version A. All right, so the version A runs at 1.2 seconds. And how about version B? So for version V, it takes 2 seconds. So the right-hand side is slower than the left-hand side. So now I am asking you to, okay, so let's see. Wait. Okay, it's annoying in a way that, okay, so now I am encouraging you to look at these 2 pieces of code and tell us why the left-hand side is better than the right-hand side. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so look at the answer. Most of you vote B and some of you vote C. So, and sometimes even though you are voting B, your B may be different from other people's B. So why don't you open the file that I just sent you and start the group discussion. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, it looks like most of you think there's only one thing right. Okay, so maybe now it's a good time to select one of the team to tell us what's going on in your discussion. Okay, again, mistakes. Well, I feel like we have one team that we haven't had today is probably the fourth team, right? So let me see if I can get it happen. No, really? Okay, so well, let's just give the fourth team a chance, right? So who is the scriber? Raise your hand. I will have the fourth team express their thoughts because I think you are the only team that hasn't. Okay, Tyler, what do you think?
We went with B1 because CPI is the only thing that changes.
Okay.
Because the nesting is different between the two programs.
Okay.
One is going to catch
So
miss a lot
if you
more
look at
versus
these two
CPI.
programs, right? So how about the computational complexity? Are they the same?
Same computational complexity, yeah.
Yeah, they are all log n squared, right? Right. And how? Sorry, they are all n squared, right? How about the instruction count?
Instruction count should be the same. It should compile
Should
down
be
to
roughly about the same, right?
yeah,
So
virtually the
and
same
how
as
about the
the
clock
code.
rate? It's the same processor, right?
Mm-hmm.
So the only thing that would change would be the CPI, right? So okay, thanks for insights. So the Rocket team thought it's a CPI, but let's really go into there and see what's going on here. So oops. So if you oops, okay, oops. Okay, so there's a tool in Linux called and actually, if you want to know what I changed after my programming, right? A good strategy is that you can use performance counters that your processor have to figure out. And if you are using a Linux, there is a perf state program that you can use. And for if you're on a Mac, there is something called time profiler in your S code. And even Intel machines, they do have the B-tune. However, if you are using an AMD machine, I don't know how you can do that because AMD doesn't have a stuff for their own processors at this point. But let's look at the Linux because it's open source and a lot of you may have it. So let's look at if I am profiling the program on Linux, what will I identify for these two programs? So now this is the screen that I have, and I do have the perf, right? Okay, I have the program called perf, and I use perf stat, and then I can run my maddA, which is the program that I just showed you. And oops, oh, where's my perf? I guess it's here. Okay, here we go. So from the output, it shows you that, okay, so the number of instructions is about this many, right? So it's about, what is this? So this is kilo, million, billion, 15 billion instructions. And the instructions per cycle, which is the reverse of cycles per instruction, is 2.73. But how about the madd dash underscore B? So if you look at the instruction count, the later version is very close. The version B is very close to the version A. It's all about like 15 millions. However, the cycles per instructions differs a lot. So that gives us the performance difference in a program that we just seen. So that's why the answer to the previous program, right? If you look at that, right, the instruction count is roughly about the same. And the clock rate is on the same processor, is roughly about the same. But what really makes the performance so different is actually the CPI. The left-hand side is better and the right-hand side gets worse. So if you want to know the real reason behind why the right-hand side is worse, we will talk about that in probably the next week or at least within 2 weeks. So don't be too panicked about like, okay, how do I know if I'm doing it right? So if I tell you the answer right now, you will probably drop the course, right? So I want to keep you in a class. So but if you look at the result, it will tell you that CPI is the main factor that making the performance so different. So in this way, you know that being a programmer, you can affect the CPI in addition to the instruction count, right? So now if you have the memory about what's going on in the first lecture, you must remember this pieces of code. So what programmer changes in the performance equation to make performance better if we enable the sort? Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like we have somewhat deviation among among you guys. So it's definitely a good chance for you to discuss with your friends to see what's going on. And I believe you guys are pretty familiar with the group of people that you have. So just open the file that I sent it out. And for this question, I would like to restrict the discussion time to be just about 2 minutes. So go ahead, do it. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now, according to the discussion, most of you think is D. So I want to invite a group to share your thoughts with us. Again, Mystic. Okay, we just give Mystic another chance. So I remember the scriber is Andrew, right? So Andrew, can you tell us what your group thinks?
Okay, so we choose D, the IC and CPI.
Why?
We not actually, conclude a reason from that, but for sure the instruction count is changed since we adding the sort.
So if you, okay, so tell me about the performance equation. What's the performance equation?
It is still the IC times CPI times CT.
CPI times CT, right? So if the execution time, so when we say a performance is better, the execution time is smaller or larger?
Smaller.
Smaller, better, right? So if I change, so in this way, how this code is affecting the IC, is it increasing or decreasing?
It's actually decreased the execution time. So since the CT is the same, and we know that the IC.
So let's talk about not talk about the instruction count. For this piece,
instruction count is increasing.
Is increasing, right? So will the instruction count make the performance better?
No, if the CPI is the same. If the CPI and CT is the same.
Okay. So what makes the performance better?
CPI actually.
Yeah, so your CPI must drop a lot, a lot to make your performance a lot better, right? So the answer to this question is actually just A. So only 13% of you got it right. Okay, thanks Andrew for telling us what your group is thinking, right? So so here's the thing, right? Programmer, this example tells you that the programmer can affect both instruction count and the CPI. However, what really makes the performance better here is the CPI. So the answer to this question would be just the CPI. So now, the last thing, right? You're being a programmer, you can actually set the cycle time because right now, our processor already exposed the interface for you to set the cycle time. And I am going to give you the demo again to tell you what you can do, right? So here, I just summarized the document it shares, and all you need to do is that so in Linux, if you took operating system before, you will know that in Linux everything is a file. So the interface that exposed is actually through the file interface, and there's something like a minimum frequency that would change the current the allowed frequency in the minimum frequency in the processor. And if you want to see what's the current frequency of the processor in Linux, you can cat proc CPU info. It will tell you everything. It will tell you everything about the processor. But right now, I'm just grab it from the megahertz, and you can see that every processor is running exactly at 800 megahertz, which is the value that about the value that we set in this file. So now, using the change frequency, I am going to adjust the frequency to let's say like 12 5 zeros. 1, 2, 3, 4, 5. Okay. Oops. Change frequency. Command not found. What command not found? Oh, you know what? the source. Okay. Oops. Wait. Okay. Let's do change frequency. What's up here? Permission denied. Okay. Permission denied. Okay, so let me copy that. Okay, so let's just do change frequency 1250. Just don't forget to change it back. Okay. Permission denied. Why is that? Sudo. Oh, you know what? This is what I have to do. Okay, here we go. Change frequency. And okay. Okay, now let's get the frequency of the processor. See, all the processor now, they are running at 1200 megahertz, which is equivalent to 1.2 gigahertz, right? So this tells you that being a programmer, you can, and when I do this again, you go back to 800 megahertz, right? So using this example, I hope it will convince you that being a programmer, you can do more than what you can do in a way that you can change, you can set the cycle time, right? So now go back to this question: how programmer affects performance? Instruction count, CPI, cycle time. You can change everything. You are the most powerful, right? So now, a lot of you care about the programming language. You always care about what programming language should I be using. So I want to encourage you to look over this question and tell me what programming languages can affect. All right, let's wrap up. Let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so looks like most of you think the answer is C. So I just want to invite one of you to tell us about like what's the one that you think is right to save our time. Okay, I have Joshua. What do you think?
Hi. So one of them that I'm confident in is instruction count, because the programming language defines the compiler, which generates the instructions, so it can affect how many get generated.
Okay, so Joshua, so you saw it's B. Okay, Jonathan, what do you think?
I actually had C. I thought you just said list one answer.
Oh, okay. So you actually had C. So what's the other one?
The other one I had was CPI. and in the kind of memory access behavior that the programming language lays out.
Okay, so Jonathan, what do you think?
I think it's 3 because you just demonstrated how you change the clock rate in Linux.
Okay, so here's the thing, right? So the thing is that changing the clock rate, it must be done by the programmer, right? If you're programming, if you as a programmer, if you didn't change it, will that affect the clock rate? Is there any programming language dare to modify the clock rate without your permission?
I don't understand.
What? So like, can the programming language change the clock rate without your permission?
I mean, no, but like if I don't run a script, the programming language can't do anything.
If you don't do it, right? So it's not a feature that programming language provides. So it's the programmer's decision to make that, right? So in this way, programming language only affects 2 of them, and that is the instruction count and the cycle time. So now the last question I want to ask you is about which of the following programming language would give you the most instruction count? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like there is a tie between C and E. So some of you think Java has the most instruction count. Some of you think that Python has the most instruction count. However, we are running out of the time, but so we will tell you the answer in the next lecture. However, before we finish the lecture, there are a few things that I want to let you know. So first of all, we again have a reading quiz due next Monday before the lecture. And if you didn't do well in the first reading quiz, don't worry about it. We will drop 2 of your least performing reading quizzes, and you will have 2 shots, but both unlimited time for the reading quiz. We took the average. And use our website for slides, Island for quizzes, assignment, Piazza for discussion. We have an assignment 1 due October 19th. Assignments should be done individually, but we do allow you to discuss with your friend. And one thing that you have to do is that when you turn it in, you just need to write down who you discussed with. So in case we see a similar answer, we won't count you as a cheating. And we will drop your least performing assignment as well. So if you decide to take this class, asynchronously, the attendance only counts as 1 assignment item. All right. Other than that, do you have any other question? Okay, if no, enjoy if you have question. What was that?
Yeah, I think in the I started reading quiz around like 9:15 a.m. in today morning,
but still it
Okay,
shows late.
yeah, okay, we'll fix that. Okay, what else?
That's it.
Okay, other than that, enjoy. Okay, Jonathan, question.
Yeah, what song just played?
Perfect.
Oh, someone was answering me. Okay, thank you.
Okay. All right, other question. Golden.
Yeah, Professor, it is showing me a late submission, but before the deadline, I've saved all the answers, but I forgot to
Yeah. I
submit
got
them.
your email. I just don't have time responding. Okay, that's okay.
Yeah, so it's fine
All
for
right.
this time, right?
Yeah, fine for this time. Okay.
Yeah, thank
All
you.
right, talk to you later. Okay, Chi. Yeah. Okay, Chi Chu.
Hello, I have a question for the assignment. Are we allowed to turn in multiple times, or is only one time turn in for the
Yeah,
assignment?
multiple times.
Okay,
Multiple
just in
times.
case, so I can turn early and if
Yeah.
I want to change, I can. Okay,
Yeah.
thank you.
Sure. All right. Golden, do you have questions still? Okay, Winston.
Just to be clear,
Yes.
it was the assignments that we can't work on them together, but we can discuss them. Is
You
that what
can
said?
discuss.
Or is that the
I mean, I cannot prevent you to discuss, right? So I just want to let you know that if you are discussing with other people, write it down. It's okay, right? Just be honest who you discuss with.
Oh, and you would want us to write it down like on our assignment or something, or on like Kaza or.
Well, so if you check the template, there is a field that you're writing that down.
Oh, okay, thank you.
Okay.
Love, fighting against all.
Okay, Yuan Hao, question.
Hi, Professor. I'm Yuan Hao Chang, and the time here is almost 2 a.m. because I'm in China now. So I want to ask you, can I just watch the recording videos rather than?
Yeah, so as I said, right, so if you check the previous slide, right, the attendance is just counted as one homework item, and we will drop your lowest homework, right? So if you decided to watch it asynchronously, all you need to do is to make sure that you have a good homework submission.
But I do notice that there is a participation score. Like
yeah, so the participation, as I said, the participation is counted as a homework item.
Counted. Yeah, but
so you have a total of 5 homeworks, right? Participation is the 6th homework.
Okay,
and we will drop your lowest homework, right? So you have 6 out of 5, and say you get 0 in your participation homework. That's okay because we only count 5 of those. So if you turn in all the 5 assignments, and if you have done it a reasonable job, it won't affect anything.
Okay, got you. Thank you, Professor.
All right, Golden, other question.
Sorry, I have another doubt. So when will you be releasing about the project, Professor? And will it be a limited time one, or will you be releasing it now and we'll need to turn it in at the end of the quarter? I just wanted to clarify on that.
Well, the project would be announced after the midterm.
Okay, so it will be a limited time one, right?
Yes.
And it will be a bit higher than the assignments, but not like a full-fledged project, right?
It's going to be a full-fledged project because you are going to accelerate a real program.
Okay, yeah, got it. Thank you.
Okay. All right. 智子. Hello?
Excuse me, Professor, I want to know from the demo, why after sorting, it can reduce the CPI?
Okay, so you will know the answer soon, but the quick answer is because we make the branch prediction well-behaved.
Well-behaved, branch prediction. Okay.
I mean, by sorting, you will make your branch prediction easier to predict. correctly.
Because it's in increasing
It's
order.
in an order, right? So
No.
yeah.
Okay.
Okay.
Fine. Thank you.
Okay. Okay. Goodbye.